Right, in the last lesson we looked at the 6 steps for carrying out a hypothesis test for continuous variables. We're going to work through some examples now. So, before we look at the example, step 1 is define the null and alternative hypothesis, and we have yet to discuss really what this one or two tail thing means. So, the example we've got in front of us, it is known that students joining year 7 have weights that are normally distributed with a mean of 70 and a standard deviation of 7.5. We'll assume they are kilograms. Now, just from that one sentence, okay, it is known that this is the great God of statistics has imparted us this information. You never argue with the great God of statistics. The examiner and he talk all the time, okay, and you get this sort of thing in exam questions. So it is known that these students do have, so all students who join year 7 their weights are normally distributed, mean is 70, variance 7.5 squared. A random sample of 90 students from the latest intake has a mean of 71.6 kilograms. Is there evidence at the 5% significance level that the mean weight of the new intake is more than 70 kilograms? That's a typical question. Right, step 1. Define the null and the alternative hypothesis. So, this is how you would write down an answer. This is how you would do it in the exam. This is how I want you doing it the whole time. Right, a null hypothesis is like, well, what did we say about the court this morning? A null hypothesis is that they are innocent. So they are just the same. It's the status quo is continuing. The null hypothesis is that mu equals 70. That is what it's always been. So the null hypothesis is mu equals 70. Your alternative hypothesis has got to be the equivalent of guilty. Now, is there evidence that the mean weight is more than 70 kilograms? So your alternative hypothesis, mu is more than 70. And if this is a less than or a greater than in here, this is what we call a one-tailed test. If I had a not equal to in there, which is implying I was equally interested in whether it was smaller than or less, smaller than or greater than, that would be a two-tailed test, not a one-tailed test. So what we're doing now, if we just think of this, okay, under the null hypothesis we've got a normal distribution curve for W where mu equals 70. What we are going to establish is a critical value and a critical region. Our critical region is going to be the shaded bit here. And what probability is associated with this critical region? 5% from the question. There's going to be 5% in there. So that shaded area there we are going to refer to as our critical region. And it is going to start at C, where C is the critical value. And we said this morning that the only thing we based our conclusion on, our evidence, was some statistical value. And if our statistical value... Now what is our statistical value going to be? What are we going to use here, do you think?
To find the probability that...
Something we've already been given, actually. What have we been given?
We've been given the mean of the sample.
We've been given the sample mean, yeah. The sample mean here is going to be our test statistic. If our sample mean is in this shaded area over here, if our sample mean is greater than C, we are going to say it's such unlikely thing that we would get that by chance. We will reject H0 and we will accept H1, that yeah, actually has gone up. Whereas if our test statistic is to the left of C, anywhere over here in like the white area, then we will accept H0. So we need to just know at the start what's going to happen. So if our test statistic is in this zone here, okay, so we should label this our test statistic. If our test statistic is in this zone here, what we will do is we will reject H0. And if you reject H0, that means you will have to accept H1. Because the chance of it happening randomly is so small, we're saying it hasn't happened at random, it really has changed. However, if our test statistic is anywhere in this zone over here, we'll say, yep, we're happy to accept H0, It hasn't gone up. Okay. So our test statistic in this question is going to be our sample mean. And our sample mean, we are told that x bar was 71.6 kilograms. So let's just go back again to our steps. Step 1, define the null and alternative hypothesis. We've done that in terms of mu. Step 2, decide on a significance level. It was decided for us. It was 5%. They told us that in the question. Step 3, calculate the critical value in the critical region. Well, that's what we're going to do now. Okay? So we know that W is normally distributed 7.5 squared. And I know that the probability of W being above my critical value is going to be 5%. Sorry, I've got this, made a mistake here. That's my W, but I'm interested over here. My test statistic is a sample mean. It's W bar, so I should have put a W bar there. Sorry, a sample mean. Sample mean. So I need to find what that C is going to be, such that this is true. Well, what is my distribution of W bar? It's normal. From the central limit theorem, it's mu, and it's sigma squared over n. N's a sample size, and we were told that's 90. So that comes out to be normal 70, 0.625 I've got here. Going back to this line here though, I don't like greater than. What can I do to that line to make it more user friendly? Yeah, if I change that into a less than and change this into a 1 minus to get my 95% or my 0.95, so what do I normally do after I've turned them into these normal things into less than? What's my normal step? Phi-ing, yeah, so it's phi of C minus my mean over my standard deviation, which is the square root of this 0.625 because that's the variance, and I'm now dealing with W bar, equals 0.95. But I want to find out C, so what would my next logical step be? Anti-phi, yeah, which means just get rid of the phi thing over here. And anti-phi 0.95, you will get to remember what this is. 1.645, that number cropped up this morning. You'll be anti-phiing 0.95 so often you will just know what that one is. And there'll be another one you'll just know what it is as well. So you need to rearrange that equation now, and if you rearrange that equation, sort of that bit you left, that bit on the right, you'll find out what C is. Has anybody done that to find out what C is? Yeah, 71.3 is correct. So I'm just going to draw the diagram I had earlier. So I've got my critical value, I've got my mean, this is the distribution of W bar under the null hypothesis. And my test statistic, my mean was 71.6, which is here somewhere. It's in my critical region. So that test statistic there is my sample mean. So what conclusion am I going to come to from what I said earlier on?
H1 is accepted, H0 is rejected.
Yeah, you actually normally say it the other way around, okay? So because our test statistic, so as, no, it's not X, is it? As W bar was in the critical region, This leads us to reject H0, which gives us no option but to accept H1, which is that mu is greater than 70. So just running through our points again from this morning, calculate the test statistic was 0.4, that was done for us, it was given to us in the question. Decide on the outcome of the test depending on whether or not the test statistics value is in the critical region, we've done. Step 6, state the conclusion in words. This is really, really important that you do this in the exam. If you don't do this, you do lose marks. So, the conclusion you would write down is this. At the 5% significance level, we conclude that the mean weight of the new year 7 has risen. And it's really important you do write down that sort of real world sentence at the end of your question. So the second question we're looking at, a machine makes bolts of diameter D, normally distributed. We know the mean and we know the standard deviation of the variance. How do we know? The great god of statistics has told us so. After servicing, a random sample of 50 bolts is taken to see if the mean diameter has changed. It's assumed that the standard deviation is still 0.015 centimetres. The mean of the sample is now 0.577 centimetres. Test at the 1% significance level whether the mean diameter has changed. Step 1, the null hypothesis. What is the null hypothesis? The null hypothesis is the status quo. Nothing's changed, nothing dodgy is going on. So the null hypothesis is mu equals 0.580 centimetres. Yeah, okay, nothing's changed. That's a null hypothesis. What is H1, our alternative hypothesis here? Look very carefully at the wording of the question. What's the sort of key phrase here? Yeah, because it has it changed? It's not saying has it gone up, has it gone down, it's just saying has it changed? In other words, it's not 0.580 centimetres. So this is an example of a two-tailed test, yeah, okay? Oh, thank you. Okay. So yeah, this is now a two-tailed test. Our significance level is given to us in the question. It's 1%. And I suggest you do a little sketch diagram right at this point. So we've got a normal distribution. Mean 0.580. And this distribution is the distribution of D bar. The sample mean distribution. We're interested in a two-tailed test, so that means we need to shade in bits in each tail where their combined probability is going to be 1%. Their combined probability is 1%. So what is the area in each tail? 0.005, which is the same as 0.5%. Yes. So in a two-tailed test, you split that significance level between your two tails. And we here will be finding a critical value, well actually two critical values. We'll be finding a critical value down here and a critical value up here. Because of the symmetry, if we find one, we can easily find the other. And we've got a test statistic. We've got the sample mean, which is 0.577. if 0.577 is in one of these tails, well, it's not going to be in the upper tail because it's smaller than the mean, so it's going to be down here. So if 0.577 is in this left-hand side tail, we reject H0 and accept H1. It has changed. If it's not, if it's in this area here, then we say there's no significant evidence it's changed. It could happen at random, you know, nothing weird's going on. So that's the diagram, and I always suggest you do a diagram at that point. So we have got d bar is normally distributed with a mean of 0.580. What's the variance of d bar going to be? Yes. Okay, because that 50 is our n value. Okay, and that mu value there, that always comes from the null hypothesis. Because we're assuming that is the case. We always take that from the null hypothesis. Okay, and as a number, if it's helpful, that is 4.5 times 10 to the minus 6. I've got noted down here. That will speed things up later on. So we're interested in finding C1. So let's find C1, that critical value. And I have the probability that d bar is less than C1 is 0.005. That is the area down there. And you guys are probably running ahead of me at this point. Okay, I think you know what to do from there. We phi it, take away the mean over the standard deviation equals 0.005. Next step will be anti-phi, yeah. Anti-phi, rearrange. So on the right hand side you'll be anti-phiing 0.005. This isn't one we use so often. I don't memorise this one. Is anybody anti-phied 0.
Minus 2.57
is correct. How did you find that?
There's bottom of the page.
Good, yeah. And the bottom of the tables you will find some of these common anti-phi ones. You don't need to look them up in the main tables. At the bottom, these 5%, 1%, 0.5% things are listed at the bottom, so you can go straight down there. So you now need to solve this equation here for C1 to find out what C1 is. It's a bit fiddly, but you will work out what C1 is. So if anybody's got that, give me a shout.
0.5745.
I agree. 0.5745. So I've just redrawn my diagram again. You've already got the diagram. If my test statistic is in the tail down here, if my test statistic is less than 0.5745, I will reject H0. But the question said the sample mean was 0.577, which is here somewhere. 0.577. So it's not in the extreme bit. So what do? We accept H0. Yeah, that's right. We accept H0. So just check through, have we gone through all the 6 things? Define the hypothesis, decided on the significance level, got the critical value, calculated the test statistic that's given to us, decided on the outcome, state the conclusion in words. So if we go back and just look at the context of the question, we can say at the 1% significance level, we conclude that the mean diameter of the bolts is unchanged. at 0.580 centimetres.